In this video, we will say about the nodal analysis. Nodal analysis. So we know already analysis is nothing but getting the responses from the branches. That means mostly current passing through the branch or voltage available across the branch. These things we need to find. That is called analysis. And here the technique is nodal analysis. And we will consider first the circuit with the independent current sources and resistors. So in our circuit, we have resistors and current sources. That's it. Now in this particular case, how to apply the nodal analysis? That is what we are going to see. Okay, that means circuit may contain the voltage sources also. Okay, circuit may contain the inductors and capacitors also. But first, to introduce this nodal analysis, I am taking the circuit which is containing only current sources and resistors. So example is, for example, I am taking here current source I1 which is connected to one resistor, and it is like this. This is I2. This is the ground. So this is the this is the circuit I have taken. Then I will take it is the first principal node, it is second principal node, and it is third principal node, it is the fourth principal node, and it is ground or reference. We know already if you have n principal nodes, then how many KCL equations are required? N minus 1. KCL equations are we have to apply. So you can remove this fourth node in the application of the KCL. So you can able to apply KCL equations at node 1, node 2 and node 3. Okay. Then we'll assume the node voltages are V1, V2, V3. Okay. Then the resistor values also will give. And this is R1, R2, R3, R4, R5 and R6. Okay. Then we'll apply now the nodal analysis. That means we have to apply KCL at node 1. What will happen? Into the node 1 current I1 is entering. So we will take like this. Entering currents is equal to leaving currents. So I1 is the current which is entering into the node 1. Then through the R2, how much current is passing? Or how much current is leaving this node 1 through the R2. That means this current I am talking. Then this is another current. And here I1 is entering into the node. So entering current is only one, that is I1. That is equal to sum of the leaving currents I have to take. So the leaving current from the node 1 and which is passing through the R2 is given by V1 by R2 plus the current passing through the R3 is given by the voltage across R3 by the resistance. So voltage across R3 is actually V1 minus V2 by R3. Like this we can write. Okay, because R3 is in between node 1 and 2. So the potential difference, the voltage across R3 is given by V1 minus V2. So this is the KCL equation at node 1. Similarly, we will take KCL at node 2. So if you observe node 2, we don't have any direct connection between independent current sources and node 2. Okay, so all the currents we can able to take leaving the node 2. So sum of the entering currents is equal to 0 and sum of the leaving currents. So leaving currents is nothing but you can take now through R4. What is the leaving current? V2 by R4. If you take R5, the voltage across R5 is V2 minus V3 by R5. And if you take R3 resistor, the voltage is V2 minus V1 and current is given by V2 minus V1 by R3. It is equal to 0. Okay, now you can apply third one KCL at node 3. In a similar manner you can able to apply, but node 3 is involving the independent current source. I2 is connected actually. So sum of the entering currents is nothing but I2 we can take. Then leaving currents related to resistor R6 and R5 we have to write. So related to resistor R6 the current is V3 by R6 plus related to the resistor R5 the current is V3 minus V2 by R5. So in this manner we have written three KCL equations, the three principal nodes. We did not write KCL equation at fourth one because already we know if you have n principal nodes the number of KCL equations required is n minus 1 only. So because the equations are involving all the P by Q forms like V1 by R2 and V1 minus V2 by R3 like this ratios are there. So instead of writing in terms of the resistances, if you write in terms of conductances, it will be easy. So what I am doing is I will take this KCL at node 1. I am rewriting like this. I1 is equal to V1 into G2. That means 1 by R2 means I have taken G2 plus V1 minus V2 times G3. So 1 by R3 I have taken as G3. Next 0 is equal to V2 G4 plus V2 minus V3 into G5 plus V2 minus V1 into G3. This is what we can take. So here already I have taken equal symbol. So it is not required here. Then the third equation will be I2 is equal to V3, that 1 by R6 we are writing as G6 plus V3 minus V2 multiplied with 1 by R5 we can write as G5. Okay, now we'll do some more modifications in the three equations. So I'm taking the first equation again, this one. How I'm writing is I will take this V1 is common. Okay, so what will you get? V1 if you take common, G2 plus G3. Okay, V1 is coming two times now, here and here. So if you take V1 is common, G2 plus G3 minus G3 times V2 is equal to I1. In this form, I am going to write the equations now. So in the second equation, if you see, do you have V1 term? Yes, we have V1 term. What is that? Minus G3 times V1 and V1 is only this one we have written. Next V2. V2 is coming many times now. So you see V2 is coming with, if you take V2 is common, you will get Z4 and G5 plus G5 and plus G3. This is about V2. Next V3 is coming only one time, that is minus G5 into V3 is equal to 0. This is the second equation. Then if you see the third equation, in the third equation we don't have V1 term. Okay, but we have the V2 term, that is minus G5 into V2 plus next V3 is coming two times, V3 into G6 then plus G5 we got, it is equal to I2. So actually because we have three principal nodes, okay, how to understand these equations means three principal nodes we have, actually four. Okay, I'm leaving about the ground because we did not apply KCL at the ground. Three principal nodes where KCLs are applied, leading to three equations. Leading to three equations. And we have three unknowns: V1, V2, V3. As we have three equations, we can calculate, we can able to solve these three equations for the calculation of V1, V2, V3. So it is possible. Okay. So anyhow, I'm taking the diagram once again here. How these equations are coming, that is what we have to understand. So see carefully now. Okay, now you see carefully. This is the circuit we have. For this, how did you get these three equations? We have written KCL equations, but you observe what is happening here. Okay, so understand clearly. Here at node 1, what are the conductances are connected? That is what you see. If you carefully observe, we did not get G1 or R1. Why? Because the current source is in series with any resistor. For example, here I1 is there. It is equivalent to simply the current source only. Because the same amount of current is entering into the node 1. So you can able to take like this. And in the analysis also, we did not include any R1 or G1. Okay, so you forget about R1. Now see carefully. At node 1, what are the resistances involved? Means, if you don't consider this R1, then what are the resistances involved or what are the conductances involved? At node 1, G2 and G3. Okay, at node 1 we have G2 and G3. So in the application of the KCL at node 1, these two are involved, G2 and G3. Okay, and G2 is related to V1 potential, but R3 is related to both node 1 and node 2. That means both V1 and V2. Okay, so this is what we have to observe. Again, I am repeating. In the application of the KCL at node 1, what are the resistances or what are the conductances are involved? G2 and G3. And G2 is specifically related to V1, but R3 is related to both V1 and V2. By keeping all these points in the mind, now how did we get this equation? That is what we have to see carefully. Okay, so without application of the KCL in the manner what we have done till now, directly you should able to write this equation. How it is possible, you see. KCL at node 1 is involving or the conductances G2 and G3 are connected to node 1. That is the first point you have to see. So you need to start like this. How node 1 is connected with G2 and G3. So I am taking G2 plus G3. These two are with the potential V1. But this G3 is related to potential V2 also. So whenever you are going to another node, then you need to take minus. So minus G3 into V2. So these are the two currents now. These are leaving the node. So it must be equal to the entering current. That is independent current source current, that is I1. So this is what we got. Now you can check equation 1 what we have written previously. This one. Now it is also same thing. Now you try to apply the same thing at node 2. Okay. So when you try to write equation at node 2, first what you need to observe? What are the conductances are connected with the node? The conductances connected with node 2 are G3, G4 and G5. So first you write them. G2 plus G3, sorry, the conductances connected with node 2 are G3, G4 plus G5. So that G3 plus G4 plus G5 connected with node 2, so that directly V2. But R3 is in between 2 and 1. So I have to take minus G3 into V1, and R5 is in between 2 and 3. So minus G5 into V3. Okay, and no current source is connected directly with node 2, so this is equal to 0. You can check, did you get this equation or not previously? Yes, I have got this equation only. Minus G3 into V1 plus G3 plus G4 plus G4 plus G5 plus V2 into V2 and minus G5 into V3 is equal to 0. So we got the same expression. Now same approach we can able to do for node 3 also. So observe node 3 first. What are the conductances connected to node 3? The conductances connected to node 3 are G5 and G6. So start writing now. So G5 plus G6 are directly connected to node 3, so that I can write like this into V3. Then this R5 is also connected to node 2, so that minus G5 into V2 will come. Then we have completed with conductances which are connected to node 3, but the independent current source is also connected at node 3. So that is actually entering current. So that I need to take here, this is equal to I2. Check with the previous equation. We got the same thing. Okay, minus G5 into V2 plus G5 plus G6 into V3 is equal to I3. So you see here, we have done previously this many steps in order to get these three equations. But now easily we have written by seeing, by observing the circuit itself, we have written these three equations. So you should able to write these three equations like this. Now just I am modifying these three equations like this. First I am writing V1. So first equation is as it is, G2 plus G3 into V1 minus G3 into V2 is equal to I1. In the second equation, first I am writing the V1 term, that is minus G3 into V1. Then I am writing V2 term, that is plus G3 plus G4 plus G5 into V2. Next minus G5 into V3 is equal to 0. Next I am taking the third equation. In the third equation we don't have any V1 term, but V2 is there, that is minus G5 into V2. Okay, plus V3 term is this G5 plus G6 into V3 is equal to I2. So in this manner I got three equations. Just I have modified, rewritten those equations. Now we can write these three equations in the form of the matrix multiplication. How? I need to take the conductance matrix which is involving the conductances, and the term related to V1 is G2 plus G3. The conductances related to V2 is minus G3 and here 0, because in the first equation we don't have V3. Next in the second equation minus G3 and G3 plus G4 plus G5 and minus G5. And in the third equation nothing is related to V1, so here 0. Next minus G5. Next G5 plus G6. These are the conductances because we have three nodes where we have applied the KCL. That means n nodes are there totally. N minus 1 KCL equations and n minus 1 principal nodes we have. Principal nodes are n minus 1 variables. That means v1, v2, v3. Variables are unknowns. Okay, so 3 by 3 matrix you will get. That means in our case n is 4. So n minus 1 is nothing but 3. Then we can multiply this one with v1, v2, v3. So if you multiply these two matrices of order 3 by 3 and 3 by 1, the resultant will be 3 by 1. So right side what is there? I1, 0, I2. That means this is indicating G2 plus G3 minus G3 0. That means the first row of this one is indicating the coefficients available in the KCL applied at node 1. That means it is indicating the node 1. What it is indicating the node 1? This is indicating the node 1 only. This is indicating node 2. This is indicating node 3. That is what you have to observe. And if you see carefully this matrix is symmetric matrix. You see the diagonal elements, whatever the diagonal elements are there, you see the diagonal elements, all are positive. Okay, and the conductances connected to node 1 are G2 and G3. That is the first element. The conductances connected to node 2 are 3 are there. G3, G4, G5. That is a second diagonal element. And conductances connected to node 3 are G5 and G6. That's why those are directly available. Then why did you get here minus G3? You are writing the KCL. This first row is indicating KCL at node 1. So this G3 is available in between node 1 and node 2. So because it is related to node 1, it came already here. So since it is connected to node 2 also, we have to take minus G3. Okay, like this you can able to observe the things. But here this minus G3 is available here. This minus G5 is available here. And this 0 is coming here also. So if you transpose that particular matrix, you will get the same thing. So it is a symmetric matrix. So you can directly write this matrix instead of writing the equation. So directly you can able to write the matrix. Then what we need to calculate actually v1, v2, v3. Okay. So this entire thing we can write simply matrix G and column vector V is equal to column vector I. As we need V, it is equal to G transpose G inverse into I. Like this you can take. Okay. In the matrix form. So if you know how to calculate the inverse of the matrix and then if you multiply with I1, I2, I3, that means if you matrix I, you will get the voltages, node voltages, you will get V1, V2, V3. So this is nothing but nodal analysis for the circuit having the independent current sources and the resistances. You can make some modifications in the circuit, but the theory is like this only. Okay. Thank you.